I now call to order the lecture portion of the Society's 2505th meeting in what is now the 153rd year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein, as some of you seem to know. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. So we welcome our members, guests, and friends to tonight's lecture by Jun Ye. The Society is grateful to PSW Full Year Series sponsors, PSW member Mike Helton and Helton Associates LLC for their support. Mike is hiding in the audience somewhere, but let's all thank Mike. And we're also grateful to PSW member Frederica DeRema for sponsoring tonight's lecture and for bringing many members to the Society. Thank you very much, Frederica. I am pleased to announce that the following new members have been admitted to the Society. Steve Jensen, an accountant with PNC Bank, interested in cosmology, quantum physics, and aerospace technology, who learned of PSW from colleagues and friends. Ann Plant, a biochemist with NIH, interested in biochemistry, biophysics, regenerative medicine, and metrology, who learned of PSW from PSW member Frederica DeRema. And Mario Digenes. Is that right or is that wrong? Digenes, thank you. Professor of Electrical and Computer Engineering at the University of Maryland, interested in optics and photonics, who's returning to PSW after a long hiatus. And he's in the audience, so let's welcome them all to membership, except there's another person, Jun Ye, who learned of PSW from the invitation to him to speak here tonight and whose interests will be clear in some part, maybe not a small part, from tonight's lecture. So welcome them all. If you are interested in membership, it's relatively easy to join. You can access the membership application on the PSW website by clicking on the Join button on the upper right-hand corner of the homepage. If you're here in the Powell Auditorium, you can access the application using the QR code on the tables at the back of the room. Everyone with a genuine interest in science is welcome to become a member of the Society. All members entitled to a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, and if they so choose, they may purchase a ribbon, which you'll see a bit later, and to wear the ribbon of the Society wherever they choose. All members are invited to receptions and dinners with speakers that precede each lecture. If you're a new member and you have not received your signed copy of the bulletin, please come see me after the lecture and I will see that you get your copy. Recording Secretary Scott Matthews will now present the minutes of the 2504th meeting in the lecture by Jason Ekberg on the Ukraine conflict on crude, ubiquitous, unprecedented modern technology applied, sadly, to war. Scott, the stage is yours.
Thank you, Larry. Good evening. On November 1st, 2024, members of the Society and guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room of the Cosmos Club. Thereafter, they joined the other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2504th meeting of the Society to order at 8:02 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, and announcing new members. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Alexandra Gade titled The Science of Rare Isotopes. The minutes were approved pending a minor correction suggested by President Milstein. President Milstein then introduced the speaker for the evening, Jason Ekberg of the United States Air Force. His lecture was titled Ukraine Conflict, Uncrewed, Ubiquitous, Unprecedented Technology Applied to Modern War. The speaker began by stating that although his talk would focus on the ways in which the Ukraine conflict constitutes a natural experiment which can serve to inform and improve tactics and strategies, it was important for him to acknowledge the human cost of the conflict, physical, emotional, and moral. Ekberg then discussed the ways in which social media and the information age have been leveraged by combatants to sway world opinion, constituting a greater influence than in any previous conflict. He argued that uncrewed aerial systems, or UASs, have provided images of the battlefield exploited by both sides to amplify successes and failures as a tool to influence the international community. The speaker claimed that the ubiquity of uncrewed air technology results in constant battlefield surveillance. Ekberg then discussed the role of UASs in asymmetric conflicts, indicating that the Ukrainian forces are outnumbered 3-1 across all battlefronts. They are outgunned by about 10-1 in terms of artillery and heavy weapons, and they have a near complete lack of air superiority. He said that these asymmetric conditions lead to battlefield innovation, which has been well demonstrated by Ukraine's use of uncrewed vehicles. The speaker gave examples of specific battlefield situations where information and supplies obtained or delivered by uncrewed vehicles allowed Ukrainian forces to hold off superior Russian forces. However, he also presented specific examples of Russian advances enabled by uncrewed reconnaissance. Ekberg then listed some of the specific battlefield techniques associated with UASs: first-person viewer reconnaissance, fire control and targeting of artillery, fire and maneuver support, and select loitering munitions. He indicated that thousands of UASs were launched each day at the height of the conflict on the Northern Front, and that this number was at least an order of magnitude larger than in any previous conflict. He discussed the fact that the low cost of UASs enabled their ubiquity. The speaker then presented what he called the Framework for Uncrewed Systems for Air, Land, and Sea. The roles and missions in this framework included individual kinetic strike, ISR operations, or intelligence, surveillance, and reconnaissance, and delivery of lethal and non-lethal payloads. The system requirements of this framework included cost, range, endurance, survivability, payload, and command and control. He discussed the trade-offs between the various system requirements in light of the specific roles and missions. Ekberg gave examples of these trade-offs for UASs used in this conflict, including UMPK glide bombs, Shaheed 136 loitering munitions, FPV quadcopter drones, and Baba Yaga's heavy bomber drones. He described the advantage of using a $10,000 drone to take out a $1 million missile. He mentioned the dependence of UASs on GNSS, or Global Navigation Satellite Systems, and the limitations associated with electromagnetic interference and jamming. Ekberg discussed launch and recovery systems, which range from a warfighter throwing a drone into the air to a catapult system to a fixed runway. The speaker concluded his talk by saying that uncrewed technology represents both a revolution and an evolution of modern warfare. He expressed the opinion that U.S. military organizations would benefit from reform, particularly in the area of defense acquisition. The lecture was followed by a question and answer session. A guest asked about the use of artificial intelligence in drone warfare. Ekberg responded that uncrewed systems are ideal for situations that are dangerous to human beings, in particular with respect to chemical and radiological hazards. He said that AI will be crucial in terms of identifying and fingerprinting these hazards. He said that these, quote, automated intelligence hazard identification systems raise no moral or ethical questions. A member asked about, quote, drone-on-drone predation. Eckbert indicated that there are many examples of drones attacking other drones, even on YouTube. He said that all of these examples involve remotely piloted drones, but that automated or AI-based drone-on-drone warfare is a, quote, ripe place for innovation. A guest on the live stream asked about, quote, mutual jamming reciprocity. Eckberg said that the action-reaction cycle of electromagnetic jamming in the Ukraine conflict is faster than we have ever seen in the past. He said that there is a tremendous amount of electromagnetic energy flooding different portions of the electromagnetic spectrum, and that this presents significant limitations to the use of commercial technology as it is generally not designed to handle jamming. After the question and answer period, President Milstein thanked the speaker, presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 1 of the PSW Bulletin. He then announced speakers of upcoming lectures, made a number of housekeeping announcements, and invited guests to join the Society. He adjourned the 2,504th meeting of the Society at 10:01 p.m. Eastern Time. Temperature in Washington, D.C., 18.3 degrees Celsius. Weather, fair. Audience in the Powell Auditorium, 52. Viewers on the live stream, 37. For a total of 89 live viewers. Views of the video in the first 2 weeks, 355. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you again, Scott, for doing such a great job with the minutes. I know it's a lot of work. Are there any comments or additions or corrections to the minutes? Hearing none, I will accept a motion to accept the minutes as read. A second. All members in favor? All members opposed to accepting the minutes as read? The minutes are accepted as read, subject to the caveat that if we get any comments online that have to be attended to, we will do so and announce them at a later meeting. And with that, we turn to tonight's lecture by Jun Ye and his lecture on the nuclear clock, scaling quantum systems for precision metrology, keeping time with nuclear transitions. Jun is a physicist with, it's either JILA or JILA, and a professor of physics at the University of Colorado, Boulder. He leads several quantum research initiatives, including the Qubit Quantum Initiative and the Entangled Science and Engineering Center. He is a pioneer in laser science and technology, next-generation experimental atomic clocks, and ultra-cold quantum gases. He invented world-leading experimental atomic clocks that tick at optical frequencies and developed clocks based on the strontium atom as a candidate for a future redefinition of the SI second. These strontium lattice atomic clocks are so precise they can be used to measure gravity, motion, magnetic fields, and many other quantities based on tiny changes in clock frequency. And he's recently demonstrated ultra-precise clocks based on nuclear rather than atomic transitions, which will enable experiments on fundamental physical principles heretofore beyond the reach of experimental techniques, and which he will be talking about tonight. He is an author of many technical and scholarly publications and an inventor in 4 patents on laser technologies. Among other honors, he is a fellow of the American Physical Society, the Optical Society of America, and a member of the National Academy of Sciences. And he is a recipient of numerous awards, which I will not list tonight so that we can get to the talk. He earned a BS in Applied Physics at Jintong University in Shanghai, an MS in Physics at the University of New Mexico, and a PhD in Physics at the University of Colorado. As usual, all questions will be fielded in a Q&A session after the lecture. So without further ado, Jun, the stage is yours.
Good evening, ladies and gentlemen. It's a little too loud, perhaps. But I just want to tell you what an honor I feel to come here to tell you a little story about nuclear clock. And this is a fairly recent development. The nuclear clock was in our laboratory. We were able to drive the nuclear transitions on May 14th. And when the student saw the nuclear transition at 11:30 p.m., he basically didn't go to sleep for the next 2 days. And you would know why. Yeah, these nuclear transitions happen to be so special. When you drive it, it lives there in the nuclear excited state for 20 minutes before it decays. So you can imagine every data point take 20 minutes, and by the time you finish scanning the whole line, it's a day. But hopefully, by the time you will say, "What a lousy clock!" It would take that much time to tell you the time, and that wouldn't be good. But in the next few years, I believe that we will trigger the revolution that will really make this nuclear clock to be a device, hopefully for portable systems that can guide you to go wherever you want it without GPS. So I want to highlight people, of course, the heroes in the laboratory. And these are 4 students, especially the leading graduate student, Chang Kun, who has been working on this project for 6 years. And both John Doyle and Tian Oi are the 2 new graduate students who joined the project, along with the postdoc Jake Higgins. And for some of you who have not been to Boulder, I know many of the friends here sitting in the audience have been to Boulder and are very familiar with the Boulder. But this is the Rocky Mountain. This is our city is named after the city, Boulder Rocks. And our lab is right here in the basement of this tower is where we discovered the nuclear clock transition. In Larry's introduction, if I may make one correction, I'm a University of Colorado employee, but actually that's not true. I'm actually a federal employee. I'm employed by NIST, just as Bill, as Charles. And so JILA is a joint institute between NIST and the University of Colorado. I should say that I have heard about PSW and the Cosmos Club for many years. I used to come to DC fairly often. And this was a picture I wanted to show because there is my dear colleague, Deborah Jing, who you will see her picture again. She is one of the true pioneers in the field of quantum gas, just like Bill Phillips. And unfortunately, she passed away, but her legacy lives on because the best atomic clock is based on technology she developed and that she gave to us. And this was in 2011, our NIST director, Pat Gallagher, and this is our beloved laboratory director, Catherine Gabby. And so I used to come to DC almost 3 times a year and just come to tell Catherine what's going on in our laboratory and so on. And every time Catherine always says, after this is finished, let's go to Cosmos Club. I will treat you a dinner there. And so, being a young person, you don't, at the moment, you didn't appreciate this. You just feel like, Catherine, I'm busy. What are you talking about dinner? I'm going to take my 5 o'clock flight, going back to Boulder, and I'm going to the lab tomorrow morning. So I don't have time for dinner. And I always felt this way. Catherine always invites me to Cosmos Club, and I turned her down every single time. And I really regretted it because I didn't get a chance to come to Cosmos Club when Catherine was still alive. And so I just want to say it was when Larry sent me an invitation to come to Cosmos Club, I immediately said yes, because this was the dream. This was excuse to come back to really pay respect to my dear colleagues at NIST, such as Catherine Gabby. She was our director, and she really played a big role in our growth as a scientist. With that being said, I want to get started. I'll first start with telling you a little bit of a time scale, giving a show here. Here's a picture. Before I tell you about nuclear clock, I want to first tell you about atomic clock to give you the context why nuclear clock is interesting. So in atomic clock, we know electrons moving around nucleus, and it moves around with a very fast speed, about femtosecond. So it's a decimal point, 15 zeros, and then you have a 1. So if I slow this down by 15 orders of magnitude, it looks like a little pendulum that's swinging 1 cycle per second. And you can consider this as your quantum pendulum. This is describing time at the fairly tiniest possible scale by nature. This is describing electron motions around nucleus. At the same time, if you think about it macroscopically, the universe has been around for about 14 billion years. And if you convert that to time, that's 10 to the 18 seconds. If you take a geometrical mean between this microscopic time scale of quantum pendulum and the lifetime of the universe, the geometrical mean is a minute. And it seems to be convenient. And the reason why this minute is important is because now in our laboratory, we can prepare a quantum state and it will live there for 1 minute. So just think about that. A quantum pendulum that's swinging 10 to the minus 15 second it's a period, but it can live there for a few minutes. That means during its lifetime, you can see 10 to the 17, 10 to the 18 swings of that pendulum. It's as if, that's what a geometrical mean tells you, it's as if you had a pendulum inherited from your great, whatever generations back, from the beginning of the Big Bang, or from God, if you believe in religion, at the beginning of the universe, and it happens to swing once per second, it would still be swinging today. That's the sort of the system that you want to use to build a clock. I want to use this slide to make us appreciate why we chase as a clockmaker, as a physicist, that long coherence time is quite important. Faster swing is also important because together the product tells you how many swings you were able to count as your time. That's what nuclear physics is going to come in. I told you time swings really fast with electron moving around nucleus. What if we go inside the nucleus and actually conquer the nuclear physics? That time scale is even much shorter because energy scale is much bigger. And what if we can have coherence time also on the scale of a few tens of minutes or a few hours? The number of swings you can have can be 10 to the 20s. And that's really where the nuclear clock's power is going to come. And I hope this slide gives you this feeling why we are working on this. And I also want to tell you the clock, I consider myself as a metrologist for NIST, but I also feel deep down, I'm a physical scientist, and really most interested in me is actually fundamental physics questions. I know sitting in the audience, we have some NSF program managers, program officers who are responsible for sponsoring LIGO. And LIGO is such an inspirational physical science achievement. And I always feel, one excuse of building clocks is to turn that into as a telescope, looking at deep into the universe. On one hand, you can control such microscopic evolution of time. Ironically, when you can do that really well, you can look at the macroscopic evolution of the whole universe. And that's really the beauty of the, micro versus macro combination. It's the telescopes, it's microscopes aspects of physical science. There are a lot of unknown physics, like what is dark matter. If we build clock network, this will be one of the most sensitive instruments we have ever built that will allow us to really look at as interferometer, just like LIGO is an interferometer. If I have a clock that can go into space satellites, I don't need to build space interferometers. I can just measure time and tell you when the gravitational wave comes if you have enough accuracy. And of course, we can use clocks to measure so-called relativistic geodesy to understand the changing Earth, the melting glacier, the rising sea levels. It's all related to time because space and time are connected. So let me I promised Larry to give you one slide or two slides of quantum mechanics. And it's the simplest possible. It's not even accurate. It's a Bohr's model. From the modern technology of quantum physics, Bohr's model is not correct. But Bohr is just amazing. You can see somebody who's just amazing giant. The intuition, however, is timeless. The only reason we can build, Bill Phillips is showing me his tie that shows the Bohr's model on his tie. Yeah, that's exactly right. So, the reason why we can build atomic clock, why we want to build atomic clock, not using mechanical pendulum, is because of quantum physics, right? And I call it Bohr's certainty principle. We always hear uncertainty principle. I want to say Bohr's certainty principle is what? Is electrons moving around nucleus has a prescribed electron orbits. And it's true whether it's in Washington, D.C., or it's in Boulder, Colorado, whether it's in Europe or in Asia or in the United States. It's the same device that we can build universal measurement tools. So this is the reason why when you look at electrons moving around the nucleus, you can send a photon to stimulate it, either emit a photon, jump it down to another orbit, absorb a photon, jump into the higher orbits. That particular photon energy is given. If you do your experiment right, that frequency should be a nature's constant, which we want to use to build a clock. But there is uncertainty principle. This is perhaps the most important aspect of quantum mechanics. And I often say, if we learn nothing from quantum mechanics, is this uncertainty principle. It's the noise that's truly quantum mechanical. Nothing else is truly quantum mechanical. The wave function itself, the wave is very much a classical language. But it's the uncertainty. It's the fact that if you put something in coherent superposition, if you have a qubit that has spin down and a spin up, as that's shown here on the screen here, spin down and spin up as the two states of the clock. And if you prepare a coherent superposition, say in this equatorial plane here, and then after it evolves for a little while, I say, I want to measure where you are, which state this atom is in. I will have no way to know in advance. And that's the true quantum mechanical uncertainty principle, which means you can put your atom in coherent superposition where the state evolves with ground state, excited state with energy difference E times T. And in fact, what the clock is doing is that you're trying to measure this phase, evolving phase, E times T. Because we know the energy between the two states very well, you can use this E times T, the phase, to measure the time. That's really what the atomic clock is all about. But you can immediately see from this picture, when you try to measure that time, because there's uncertainty, when you let it evolve for a little while, and you're trying to say, where are you? Are you in the ground state or excited state? Well, there's some uncertainty coming out. And that is a fundamental limit of how well you can measure time. So quantum mechanics gives us both certainty and uncertainty, as life always does, yin and yang, both parts. So we build lasers to try to probe these kind of a coherent superposition of quantum states. And we build phase coherent lasers. This is actually the one piece of technology I'll tell you about. The laser turns out to be one of the key critical technology for unlocking nuclear secrets. So if I use a phase stable laser, what I'm doing is I set the electron motion in place by creating coherent superposition, and then wait for this coherent evolution that's going on. This is a phase evolution, which is nothing but this term ET, energy, or you can call it frequency times time. That's the phase accumulation, and eventually I want to make that a measurement. And because of this uncertainty principle, if you just measure one copy of the atom, there's a lot of noise. There's not a lot of uncertainty. So one way to do this is you build a system up with many, many atoms. So you can measure quantum pendulum, not just one, but millions of quantum pendulum at once. And the noise is so-called, the quantum uncertainty principle is called white noise, meaning the noise scales with square root of the number of measurements you make or number of quantum particles you put it in. So the bigger the quantum system, the larger the number of quantum particles you have, the uncertainty goes with 1 over square root of how many atoms you have in the system. Some of you may have heard about quantum entanglement. So there's two ways to scale the system up. One is just keep making N larger and larger. Another way, it's called a quantum entanglement. I just want to tell you a little bit about this, and then we'll put this aside, and we'll focus on making N larger and larger, kind of a story. But what entanglement actually means is that if you can somehow make N copies of atom to be correlated, in the sense of each atom has this intrinsic quantum noise, but what if I get N copies of all the atoms to have their noise behave exactly the same way? Then instead of having N copies of noise, you have only one copy of noise, because every atom, when you flip one coin, every other coin flips exactly the same way. That's the so-called quantum entanglement. If we want to discuss that, maybe we can do another discussion at dinner and so on later. But today's focus is not on quantum entanglement, except you take my word for it. The most important aspect of a quantum entanglement is the noise. When you can entangle two atoms, what that means is the noise fluctuation between two atoms are the same. And this is the same principle people use to build a quantum computer, to do quantum communication, in our case, for clock. And you can immediately see why entanglement is so important for clock, is because if there's only one copy of noise, but you still have n copies of a signal, well, the signal-to-noise ratio now scales as 1 over n, or rather, signal-to-noise ratio scales with n, but the uncertainty of the phase measurement scales as 1 over n, as I kind of use a cartoonish way to show this uncertainty has now been shrink down, skinny, so that you can have a better measurement of where the phase evolution is. And this all comes from the entanglement can hide each other's noise. At the moment, the entanglement is what we are working on. It's not yet caught up with the state of the art of atomic clock, where we simply just by scaling up the numbers. But this is very interesting area of quantum science, especially for information processing and for communication, that we want to keep working on that as well. The next thing I want to tell you, so I told you about these necessary ingredients of have lots of particles being able to control their quantum states and then average them away. Well, the next thing I need to tell you is how do we actually physically do those experiments? And as we all know, if you have a physical trainers at home, they will tell you, keep moving, keep active lifestyle, you will live longer. And that's certainly true. That's Einstein's relativity theory. If you build clocks based on atoms moving around in a jar, which means in the old-fashioned days, we have cells with atoms and so on, then moving atoms are going to tell you slower time as far as a stationary observer is going to see. So you have clocks which are telling you a different time between different atoms. Furthermore, Einstein has another part of time dilation, not just motional time dilation. There's a so-called gravitational time dilation. At different elevations, these atoms also move at a different time because of the curvatures due to the Earth, due to the Earth's gravity. So if you don't control the atomic motion, you can end up having lots of atoms to giving you the time, but every one of them is giving you time slightly differently. And that's not a system of clocks you want to build. What you want is to have millions of atoms. Every one of them are quantum state engineered to be identical. And then you should be able to really make a very precise time measurement. So how do we do that? Fortunately, we have a lot of pioneers in this field. And it's actually fascinating. If you look at our field for the past 4 decades, from 1980s to today, there were actually a lot of Nobel Prizes being given. And that's not very often, but there's to this field, there's a lot of Nobel Prizes being given. That's because, initially when Dave Weiland said, well, I can trap a single ion, and I can use this single ion to make an atomic clock by doing laser cooling, by cooling this atom such that I can engineer quantum states. That sounds a little bit of fantasy, and that's why he got a Nobel Prize. It's a real physics question, but it turns out this is now just common day technology that we all use. But Dave has one atom, right? One ion. And then we have one of the pioneers sitting in the audience here says, well, why don't we cool down lots of atoms? They are neutral. They're not charged. So you can put a lot of atoms in a single volume, because if you have ions, they're going to repel each other due to Coulomb charge. So this is the invention of laser cooling, also done in the late 80s, 90s, and so on. And very quickly, this technology, Bill Phillips, Steve Chu, and Claude Canton-Junji, led to yet another revolution, the so-called Bose-Einstein condensation. This is a quantum matter that's visible. You can actually see almost with your naked eye, where thousands of atoms, they all occupy the same quantum state and condense in the ground state of some sort of harmonic trap, because every atom is bosons. They love to hug each other, and they just occupy the same ground state and form this macroscopic quantum coherent state. And so for that, these 3 gentlemen won the Nobel Prize. I think Debbie, my colleague Deborah Jing, should certainly have won the Nobel Prize. Unfortunately, she passed away a little too soon. She was the one who created the degenerate Fermi gas. And so fermions and bosons are 2 fundamental different particles, where bosons are very social, love to jump on top of each other. Fermions like to stay away from each other a little bit, or at least orderly, one person occupying one seat, just like you have here. And so she was able to study this almost like a little neutron star in her lab, because she was able to cool down the temperature so much that every atom is occupying below the so-called Fermi temperature in an orderly fashion. So what I'm highlighting this work is to show you now we have very good control of individual atoms. And what if now we can start to dream about why don't I put these atoms in a very ordered fashion, one by one, creating a crystal made by interfering laser beams. And I can put atoms one by one. Also, it looks like just a condensed matter system. It's a crystal, except you created this from scratch, from a gas. But every atom is removed with entropy. And so you have exceedingly low entropy systems. And you can, in principle now, just like I mentioned earlier, you can create many hundreds of thousands of copies of atoms with every one of them look identical. And you can use this to make clocks. Simple enough, sort of a motivation, yes? It took a couple of decades of technological development to finally be able to put these atoms individually. So there's one more trick I want to tell you for the atomic clock. The last trick is, well, in order to trap these atoms by laser light, this is a technology actually invented in the Bell Labs by Ashkin, where it's called an optical tweezer. You may have heard about this. You can focus a laser beam into the middle of the vacuum chamber. You can pick up one atom or one molecule at a time, or even one dust particles. But ordinarily, these laser traps will distort the energy separations of the two clock states. Another way of saying is the reason why atom can be trapped is because a laser is creating a spatially dependent AC stock shift. And that's why they are trapped in the middle of the vacuum due to the laser focus. But the excited state and ground state are not necessarily being deformed the same way. So you can think of as if the way that you're creating the system is that each individual atoms now have their electronic orbits being distorted differently. So this, again, is not good because you're making identical atoms to be not identical. It's going to make a clock running at a different speed. And this idea was, then this particular challenge was solved by the next idea, where it was actually proposed by Hidetoshi Katori at the University of Tokyo around 2000, as well as when I was a postdoc working for Jeff Kimball at Caltech. We had similar ideas. The idea being, well, let's find a particular laser wavelength. And it sounds exceedingly simple-minded idea. Let's find the laser wavelength. When you create a trap, like this little blue ball that you're seeing, it's created such that the excited state and the ground state that represents the clock states, they experience exactly the same shape and form of the optical trapping. So now, in that case, the clock states is looking like as if every atom looks identical. And so once you have this idea, now you can finally assemble this artificial crystal of atoms, and you can then do laser cooling and trapping, and do quantum gas engineering, and finally you can do clock experiments. I took a pain to explain to you why it has been so hard. And the atomic clock is good, but it took a lot of technology in there. But it has delivered a really amazing performance. The state-of-the-art clock performance based on these atomic clocks has now reached the level of measurement precision in the mid-10 to minus 20, meaning due to Einstein's relativity effect, gravitational redshift, if the clock moves by one human hair width of distance on Earth, the time will slow down or speed up, and you can actually measure that. The systematic accuracy, this will be needed if you want to do redefinition of time. You can see both trapped ion clock and neutral atom clock has entered about 10 to minus 18 range for you to say, I can make a measurement here in DC, I can make a measurement in Boulder, they will agree at that level. And even entanglement is starting to play a role. Remember, I mentioned very, very briefly of a quantum noise can entangle with each other. And so we can now start to put entanglement into the state-of-the-art clocks at the 10 to minus 17 level, not at the state-of-the-art of 10 to minus 20, but you can start to see that kind of a technology of quantum entanglement can start to come in, play a role at a very competitive level, and it will require us to continue to push that game forward. And this is a good place to maybe stop for a little bit to just think, okay, here is an atomic clock based on electrons moving around nucleus. It's exceedingly fragile because electrons can be easily perturbed by external magnetic field or black body radiation, or just magnetic field, electric field, laser, unwanted laser beams, and so on. The electron is very easy to be polarized away. And so that's why we took a pain to cool the atoms down. We put them inside vacuum. We control them with laser field. We do not want them to touch any solid surface because it will have van der Waals interactions and so on, to shift energy levels. It's just delicate device. So it's some of the most precisely measured time device that we have constructed, but it's not yet ready to move out of the laboratory or make the wristwatch for you to enjoy. And so this is a place I want to now move onto nuclear clock. Why the nuclear clock can potentially solve that problem. But more than that, nuclear clock also can allow you to continue to scale up the number. So let's think about nuclear clock. But I also want to look back. In fact, atomic clock learned a lot from nuclear physics. You are the nuclear physicist here, Federica. That you in some sense, in the 50s and 60s, when the mass power spectroscopy started, when people can actually understand, well, there's a nuclei, you can absorb gamma ray photons, and the recoil momentum being absorbed by the entire crystal, and they can do very high resolution spectroscopy. At that time, there's no optical clock whatsoever in atomic physics. But I think we learned, especially the pioneers who did a trapped ion, like Dave Wineland and so on, they took that to their heart, this mass power spectroscopy, where the recoil momentum needs to be suppressed. Whenever you have a quantum absorber, if it absorbs a photon, or if it emits a photon, there will be a recoil. I do not want that recoil to be there. How do you do that? That's what the nuclear physics told us with the mass power spectroscopy. So that's why when trapped ion started, they immediately worked on laser cooling and trapping to confine a single ion at the bottom of the very deep trapped ion trap, such that the confinement frequency or spring constant is much larger than the recoil force. So when the photon comes in, try to recoil that ion, when ion gets absorbed from ground state to the excited state, that recoil momentum is not allowed. And that's a key thing to allow you to do high resolution spectroscopy. And you can think of the clock I told you about, the optical lattice, where we can put lots of atoms in there. It's built on exactly the same principle. The trapping potential of this light field is so strong. When I having a photon come in to excited atom from ground state to the excited state, that recoil momentum is absorbed by the lattice, not by individual atoms. And that's a key, again. The motional degrees of freedom is separated from the internal degrees of freedom. So can we then give back to nuclear physics? We learned so much from nuclear physics. Can we turn the mass power spectroscopy was great, but it was all done in an incoherent fashion. Can we give this back if we can do coherent spectroscopy on mass power? And that's what a nuclear clock is all about. So when mass power, he's showing here, is on the right-hand side. With the mass power spectroscopy, if you think about it, is really looking at a very, very simple energy level diagram. You can see there's a nuclear decay, and then the nuclear decay can also decay further, give out gamma ray at a kilo eV kind of energy scale. If this gamma ray happened to be picked up by another nuclei in the ground state, then this gamma ray can be absorbed. And this is the so-called mass power spectroscopy. And this absorption comes with recoil free because the entire recoil momentum is absorbed by the entire crystal. And the reason why I want to highlight this yet one more time is because, in fact, it has very proud history for atomic physics. The very first confirmation of so-called gravitational red shift was done by mass power spectroscopy. This was done in a famous experiment in Harvard. this by Pond and Replica in this building. I think I forgot it. Yeah, Lyman Laboratory of Physics, and the building's still there. And they showed me actually that I gave a lecture in Harvard recently. They showed me that building where you have a nuclear absorber in the basement, and the gamma ray photon will go up. Nuclear emitter is in the basement, and the gamma ray photon will come up to the top floor, where the gamma ray is going to be absorbed by the nuclear absorber here. And what they were able to measure is that the emitting frequency and the absorbing frequency was slightly shifted. And that's where they called it red shift, as if a photon is losing energy as it travels against gravity. But of course, that's a perspective. This is really because of the metric coordinates have been changed due to the curved space of the gravity of Earth. And I just showed you experiment in atomic physics. We cannot measure the clock being different over just a few hundred microns of distance. You can see the same thing. You can see time is different. So I always say, well, there's always a nuclear atomic connection for fundamental physics. But I think the connection is not just got much stronger. Now, with a nuclear clock, we can finally, using nuclear transition itself, to probe these kind of fundamental physics. So I'll tell you a little bit of that story now. How do we build a nuclear clock? Well, if you look at the nuclear energy levels versus atomic energy levels, you will see atomic energy levels typically in the EV scale. It's a wavelength, visible wavelength our human eyes can perceive. So that's why we build lasers, to be able to drive these electronic transitions. In nuclei, the nuclear transition is typically in the kilo EV and even in mega EV scale. And there's no laser available. You need to go to user facilities, synchrotron, X-ray, gamma ray generators. And in there, actually, the only thing that's coherent you can think of is this, you have this driver that can actually move this little crystal with a nuclear target in there. You can move it with a velocity back and forth. And that will give you Doppler shifts. That's how they tune the resonances back and forth, because the gamma ray is incoherent and it's fixed in energy distribution. But you can do reasonable spectroscopy just by doing these kind of a velocity modulation process. So you can see the key thing has been the lack of coherent radiations to drive these kilo EV scale. And we still don't, the nuclear transition I'm going to tell you about is not a kilo EV scale, it's a 10 EV scale energy. And that's actually being lucky. So you can see that in order to build a nuclear clock, we want to have energy levels inside the nucleus that can be accessed by a laser. And if you can do that, if you can build a counter, then suddenly you have the entire system. You can measure the energy levels with a coherent laser beam. You can count the laser frequency, and that seems to be like the quantum pendulum idea that I was telling you about, just like atomic clock. And unfortunately, if you look at these low energies nuclear transitions, you can see most of the nuclear transitions are hovered around here, a mega EV scale. And that's why nuclear physics is a high energy physics. There are a couple candidates. In fact, we were initially very interested in uranium transition. It turns out to be at a 14 nanometer. It's a near 100 EV. There's another one, the thorium-229 metastable state, isomeric state, that its energy level is about 10 EV above the ground state. 10 EV is close enough where you can start to dream about, well, maybe I can build a laser that can actually drive these nuclear transitions. And so that's where we started actually building the system about 20 years ago. Initially, the goal was to actually drive a uranium transition until the thorium transition really got heated up, and it's much easier to access. And so I will tell you a little bit about what kind of a technology we were able to use to produce coherent light in the vacuum ultraviolet or extreme ultraviolet that allow you to directly drive these nuclear transitions. But if you can build a nuclear clock, the abundance of opportunities for both science and technology. One is, I think, in my very first slide, I emphasized this quality factor Q, meaning how many oscillations in its lifetime you can measure. And for nuclear clock, you can potentially get to 10 to the 19. And so that's very attractive to build a very highly accurate clock, for example. The second part, I think, to me, the most exciting aspect is actually the scalability, where because the nuclear transition is unlike atomic transition, where you have electrons, you're now actually looking at energy level structure within the nucleus. It's much, much better protected. It's not immune to perturbation, but it's much better protected. You can start to wonder whether it is possible that instead of this artificial crystal that I made with laser light on atoms, I can just embed these nuclei in the regular crystals, and you can have much, much larger numbers of nuclei being investigated by the laser beam. Instead of 1 million atoms, maybe I can have 1 Avogadro's constant number of nuclei being employed for clock. And that's just incredible scaling on AIM. Bill and I were joking during the dinner time. By the time you can have 10 to the 23 nuclei to be working in your clock, well, we don't really need a quantum entanglement. It would be just amazing clock just on its own. And maybe that's the clock we'll use to probe quantum gravity. It's a very sensitive probe for fundamental physics. And I will actually if I have time, I'll come back to this point where as you start to drive the nuclear transitions, now inside the nuclei, we know that energy levels are balanced between strong force and electromagnetic force. So even though I'm driving 10 eV energy, actually it's sitting on a pedestal of a kilo EVs of energy. So if something is changing with electromagnetic field, if you want to compare QED physics or QCD physics, some people believe fundamental constants may not be constant. This provides a new platform to look for possible variations of fundamental constants. And finally, I must say, this is a new degrees of freedom of quantum. If I have better lasers, I can start to turn this nuclear transition into a qubit. And maybe in the future, the clocks and the quantum computer, they're always connected. I can drive these nuclear qubits and turn them into interaction. Maybe my quantum computer turns out to be coming from nuclear physics. Who knows? But I'm absolutely a believer. If you can build the best atomic clock, you're also very close to build some of the best quantum computer. It's not exactly the same, but the technology base is the same. So the thorium transition actually has had a long history in nuclear physics. Started by some Russian scientists observed that there are 2 gamma rays coming down when the thorium was decaying. Those 2 gamma rays are both in tens of kilo eV kind of a range, but those 2 gamma rays were hardly separable in energy scale. And they did precision measurements with 3 digits or something. And they were able to see, okay, the 2 gamma rays with kilo eV energy, maybe they're different by 3 eV. That indicates there must be 2 energy levels down near the ground state. There's a ground state, there's another metastable state sitting somewhere about 3 eV. This idea was, I think, in the 70s. People already did, from the Soviet Union kind of days, you look at the literature, people are talking about that. And then so people were trying to look for this transition for a long time, and nobody found it. Some people put it on revisited this gamma ray, try to do a more precise measurement of the splitting of the 2 gamma ray decay photons. And there's some spread, and they don't really know where it is. And the people start to lose interest because, okay, you have to say there have been a nuclear state that's very close to the ground state, but nobody found it. This was really until around 2010, there were new measurements coming out from Los Alamos and actually from Europe. Nuclear physicists start to do much more precise, higher resolution measurement of a gamma ray spectrometer. And they said, well, hold on, the energy is not 3 eV. Maybe it's at a 7 point something eV. It was 7 or 8 eV. And that really re-stimulated a lot of interest in the community to go back to search, to do more precise gamma ray experiments. And I want to say one landmark experiment was last year in 2023 in the summer. This experiment was done at CERN in Geneva, where they finally were able to show that you can have these francium decays into thorium, and it embedded thorium into calcium fluoride crystal. And they waited for a little while. They can actually see there's a photon coming out. This photon is apparently fluorescence photons due to the decay of the metastable state of thorium down to the ground state. So this, you can consider this is the first observation of radiative decay of photons between the nuclear states. That's for thorium, I should say. Of course, people see gamma ray photon decay all the time. And they were able to pin this down to relatively good small uncertainties. And that immediately jumped us. We actually have been working on something, a target that's not based on calcium fluoride crystal. And towards the end of my talk, I will tell you about thin film work that we have been working on for the past 5 years. But when we heard about this crystal result, we immediately contacted the university who provided that crystal to Vienna, to CERN, and that turned out to be a group in Vienna that was providing these crystals. So we contacted them, but it took a while for a nuclear material to transport across Atlantic Ocean to come to the US. Meanwhile, I think earlier this year, there were 2 experimental observations of a direct laser excitations. Instead of watching the fluorescence decay, people actually put on something like a 20 gigahertz line with laser and just drive it with a 4-wave mixed laser device. One experiment at PTB in Germany, the other experiment actually soon after that, about a month after that, in UCLA by Eric Hudson's group. And both groups were able to pin this down further because now you're using 20 gigahertz laser to drive the nuclear transition. And so you can see actually the line shape by scanning. There's some hysteresis because the lifetime is very long, but nevertheless, you can pin this point down to a few gigahertz. What's interesting about this is made us further believe, much more convinced that what the path we were on will absolutely see these nuclear transitions with much higher resolution, with absolute frequency determination very quickly. But now I'm going to tell you, how do we build a laser that has much higher peak power at a VOV, spectral power at a VOV, vacuum ultraviolet, and also very narrow spectral line at the same time, that being able to drive these nuclear transitions. Remember, I told you that those nuclear transitions are supposed to live for 20 minutes. And if you take 20 minutes to invert that, the line width should be on the order of tens of microhertz instead of tens of gigahertz or 20 gigahertz or 10 gigahertz. So there's a lot of room to gain. You also notice there's no structure of a nuclear transition inside because the line width is too broad. So whatever the structure of the nuclear sublevels is not being shown here. So I want to tell you a little bit about how we developed this vacuum ultraviolet laser light that has very high resolution. So if you look at this electromagnetic spectrum from the visible spanning all the way out down to X-ray, this is a 10 nanometer all the way out to 1 micron. In the visible part of the spectral range, there had already been a revolution. It's ongoing. This is so-called optical frequency comb. And this is one of the most amazing device. It's a laser that's pulsed, but the pulse is coming out with such regular intervals, and you can control the electric field underneath each pulse so well. You can produce basically a rainbow color in the frequency spectrum with every single line very precisely nailed down to some of the most precisely stabilized lasers. So this technology allows you to connect CW laser that's meant for doing precision spectroscopy with ultra-fast laser, where you can have a peak power fairly large to do nonlinear frequency conversion, but still keep the phase coherence as good as a single colored CW laser. So this suddenly freed us up to be able to use laser tools to do whatever spectroscopy we wanted, not only in the visible, but potentially also in the extreme ultraviolet, because I can do nonlinear frequency conversion much more efficiently if I can focus all the power, all the laser power into a very short amount of a time period so that my peak power is much larger. Or vice versa, I can also convert all the laser light to the far infrared and do a lot of molecular spectroscopy. There's a lot of applications on that front. So that's good. On the other hand, anything below 200 nanometers has been at more or less a virgin landscape. There's no high-resolution lasers available. If you want to really go in there to look at structures of matter, you have 3 electron lasers is available, but it's not high-resolution laser devices. Synchrotron radiations are also available, but they are all broadband. So how do we do this? Well, we also have had pioneers in the field of optics who have been doing the so-called high harmonic generation. And these are the 3 pioneers who shared the Nobel Prize last year on the so-called attosecond physics. What attosecond physics is all about is if you have a laser that the field is so strong, a single pulse, the field is so strong that you can actually ionize, or another way of saying you can distort the Coulomb potential of the atom so much the electron will be actually liberated from the nucleus and coming out. And it's going to be dithering inside with the laser field, gaining some pondermotive energy, and then recombine with the nucleus. In that process, seemingly very violent, you can generate high harmonics. This is the 7th harmonic, 9th harmonic, 11th harmonic of this fundamental light that's driving this process. And this can allow you to build many, many harmonics, go well into VUV, extreme ultraviolet, even soft X-ray regions. And you can make the pulse so short, you can start to look into the so-called attosecond physics dynamics. But I'm not actually that interested in attosecond physics, to be honest. I'm just very interested in this physical process of converting frequencies from one spectrum to the other. What I want is a high resolution. And this system does not give me high resolution because each harmonic is the entire bandwidth of the visible light. What we need is to have system which allow you to generate these high harmonics one after another in a phase coherent fashion, exactly from these 2 pioneers we learned, Ted Hensch and John Hall. Jan happened to be my PhD advisor, by the way. And they won Nobel Prize for this frequency comb. And the trick on the frequency comb is to be able to send repetitively the pulse with phase coherence. And therefore, because it's a phase coherent between these repetitive pulses, you can reconstruct in the frequency domain as individual comb lines that's separated by exactly inverse of the period. So if it's 10 nanosecond pulse period, you will have a frequency comb line of 100 megahertz. 100 megahertz is inverse of 10 nanosecond. But you can immediately see why this is a very difficult thing to do, because in order to just do that, in order to do this high harmonic generation, this peak power, or rather I should say peak intensity, the electrical field corresponding to this distorting the Coulomb potential for electron to come out needs to be at 10 to the 13, 10 to the 14 volts per centimeter, or 10 to the 13, 10 to the 14 watts per centimeter square. That's the intensity you needed. And so then you can reach the electrical field that's comparable to the Coulomb force that's binding the electrons around the nucleus. And if I ask you to give me 10 to the 13, 10 to the 14 watts per centimeter square pulse every 10 nanosecond, you can immediately put out the little envelope, do a back of the envelope calculation. How much power do you need? You need 100 kilowatts or tens of kilowatts. And there is no amplifiers available to do this. But actually, back in 2004, we came up with this idea where what if you don't have an active amplifier? You just use a cavity circulating the power. What I mean by this is, if I make a pair of mirrors, if we make the distance between the pair of mirrors just right, then there's a so-called optical cavity modes separated by the so-called free spectral range. And this is the repetitive modes, just being light is bouncing back and forth between 2 mirrors, there will be resonance coming out. The same physics as violin and so on. It's a resonator physics. And my laser, my pulse laser, remember I mentioned, it also comes with a certain repetition frequency. What if I match the repetition frequency with the free spectral range of the cavity? Which will mean every single comb component of my original laser is now mapped into the cavity. Each mode finds its own resonant structure of the cavity, which means I can copy the entire frequency comb from outside of cavity to the inside of the cavity. But once I'm inside the resonator, I can build up the power by the finesse, by the Q factor of that resonator. This does not cost energy. It almost sounds too good to be true, but it can only work inside the cavity because what you're doing is the cavity is your delay line, coherent delay line. You're just building up the power one after another. So you have to wait a lot of, it's essentially you can think of, it's just coherently building up the energy on top of each other. And so inside the cavity, it's possible you can actually have tens of kilowatts of these pulses running around with a repetition frequency of 100 kilohertz. And perhaps that will give you the system that you can actually do high harmonic generation. And that's exactly the experiment in 2005 showed. That we instead of using a pair of mirrors, we use 4 mirrors for technical reasons. We made a bow tie, but that's not important here. The main point is to say that we were able to match the infrared frequency comb mapped inside the cavity and then build up its power so much that every single pulse we can ionize the sample of the xenon atoms in the tip here. And so you can now, every 10 nanoseconds, you generate a pulse. And it turns out these pulse to pulse is actually very phase coherent. This was a pleasant surprise. This attosecond physics turned out to be really coherent. And so suddenly we have a chance now to convert from visible frequency combs into extreme ultraviolet frequency comb. That makes sense? Okay, Bill is nodding. So suddenly we have this capability that we can have a frequency comb not only in the visible, but into the VOV extreme ultraviolet. And in 2012, we did this experiment to test this. Do we really have a comb structure? At the time, we were not ready to explore nuclear physics. We just use atoms. So you can see that I have made a little animation here for you. The frequency comes in, that's why it's called a frequency comb. It's kind of repetitive frequency markers. And if you want to do spectroscopy, all you need to do is to scan this frequency comb back and forth a little bit. This animation, one of the comb line will hit that resonance, and you will see that transition that takes place. And so we did this experiment with very high-lying electronic states in atoms. In this case, we actually tried 2 different atoms. One is xenon, the other one is argon. Neon and argon, excuse me. And we were able to see those transitions at 82 nanometers, at 63 nanometers, these individual frequency combs. So we know that we are ready when the nuclear transition becomes, when we have a nuclear material in our hand, we should be able to use this frequency comb structure to drive it. And I want to point out, we were very close to like 50 nanometers, but remember the uranium transition is actually at 14, so we are not quite there to drive the nuclear transition of uranium. I would love to, because that would really indicate it's not just one special nuclei, we can make a nuclear clock. We will turn this into like atomic physics. We should be opening the whole chapters of nuclear physics for precision investigation. And so fortunately, Thorsten Schum's group at Vienna finally was able to send a crystal to us on May 10th. But I want to highlight the contributions of both Thorsten Schum's group, because for them, they have been working on this building a crystal for the past 14 years. And that's also a heroic effort. And I also want to highlight the work by Eric Huddison's group here at UCLA. They have been also working on the crystal for 14, 15 years. And these are the 2 groups can provide these kind of a crystal device. And it's amazing if you look at the doping concentration of a nuclear, how much nuclei you have. It's 4 times 10 to the 18 per cc, while the atomic gas I was telling you about, Fermi gas, the boson gas, we have 10 to the 12, 10 to the 13 per cc. So this is many orders of magnitude, plus it's inside the crystal. You don't need to cool anything down. It's in room temperature. So we, as I mentioned, we received it on May 10th, and a week later, less than a week later, we saw nuclear transition. And this is the kind of the device. This is actually the crystal. To tell you, we don't need a fancy laser cooling and trapping. It's a crystal sitting on a crummy amount of copper that we put together with a machine shop just overnight. And this is just another plate to stop the VUV light from forward propagating. And this whole black surface here, it's actually a little parabolic mirror, so that when the fluorescence coming out of the crystal, we can catch this. And so now it's the same trick. There's a nuclear transition somewhere, and we have this frequency comb. If my frequency comb bandwidth is matched with the uncertainty of where the nuclear transition might be, then it's guaranteed almost if I scan it, one of the comb line is going to hit it. And again, a cheesy animations like this. You just do scan like that, you should see nuclear transition. And indeed, this was what I was telling you about, that we have this crystals in the middle, and we have this parabolic mirror to collect all the fluorescence from the nuclear transition coming off to our PMT detector. And so this is, in fact, the first night when we actually saw the transition, it did not come with one transition. It comes with multiple of them. And it was very exciting. The line width is very narrow. These are not 20 gigahertz transitions. These are now 100 kilohertz transitions. And they are extremely long-lived. So this is actually showing you the time we waited after we, for example, we drive the crystal with VUV light, we turn off the VUV light, and we just wait for the fluorescence to decay, because there could be color centers that's decaying. But those electronic color center typically decays much, much faster. This nuclear transition decays, this is actually time scale. You can see over the time of 200 seconds, it hardly decayed. And turns out that the half-lifetime of that fluorescence decay was 700 seconds. So that's all very nice, but it's painful to take the first set of data. And you may be asking you may ask one question like, yes, it's easy to have one line to scan off a nuclear transition. How do you know which line? How do you know what frequency? Right? There are so many lines, there are so many possibilities. How you can be sure you can determine the absolute frequency? And it turns out that's a relatively easy question to address. We can use 3 different repetition frequencies, and here's what I'm showing you. We can actually tune our frequency combs with different repetition frequencies. And you scan these with different repetition frequency, you scan the transitions. Because you know the exact relationship between these repetition frequencies, you can derive a very simple algebraic equation. Basically, it's telling you if I make my repetition frequency a little larger or a little smaller, then as I scan over this nuclear transition, the frequency will be shifted. But how much the frequency is shifted is related to the mode order number. So we can use this technique to actually determine what the mode order number n is. And I don't need to get into the detail. It's just that it's telling you it's actually relatively straightforward to determine which model line that's actually driving it. And in the end, we can have 3 different repetition frequencies driving, and they show up at different locations. But when we put it in the right mode order number, they all jump on top of each other and determine where the center frequency, absolute center frequency is. So this is kind of the line center, the line shape we typically see. And it's about 100 kilohertz wide. In a room temperature crystal, if it's an electronic transition, this will be tens of gigahertz. So 10 kilohertz, I think it's not a nuclear transition line width of the crystal. By some rough calculation of it should be a few kilohertz kind of line width. And so we believe it's our laser, and we need to do better laser stabilization of our VOV comb. And this is showing you the fluorescence decay lifetime I was telling you about. And here we took a data for, it's actually quite amazing. In atomic clock, we never do that. But in nuclear clock, this is almost 1 hour. You drive it, you wait for 1 hour for this fluorescence decay to come to the background counts. So strontium that, because we made the frequency comb based on our strontium clock, I told you about the strontium clock, and in strontium clock, we already have a frequency comb driving it. And now this frequency comb has been frequency coherently upconverted to the VOV frequency comb, which with one of the lines driving the nuclear transition. Suddenly, the atomic transition and nuclear transition are now frequency connected in absolute frequency sense. And in fact, in the future, we would like to see phase coherent ticking of a nuclear transition with atomic transition. And this was immediately, this allows us to write down 13 digits on the ratio of the frequency of a nuclear transition versus atomic transition. But more exciting to feel like, what can we pay back to nuclear physicists a little bit? we were able to see those 5 transitions, right? And I didn't comment on where these 5 transitions coming from. It turns out the ground state of thorium has a nuclear spin of 5½ The metastable, the isomeric state, has a spin of 3½ And they have a nuclear quadrupole moment. Inside the crystal, there's an electrical field. This electrical field is going to split the quadrupole moment due to the electrical field gradient. Electrical field gradient times quadrupole moment will give you the splitting. Almost like you have a Zeeman structure that can be split by magnetic field. And so this allows us to actually measure 5 different transition frequencies that's showing you this is nothing but these sublevel transitions of a nuclear quadrupole structure. What does that mean? Well, we can't put it in this, we open up a nuclear physics textbook. It tells you, okay, there's a Hamiltonian that describes, here's a nuclear quadrupole moment Q interacting with a gradient of the electrical field inside the crystal. And that's the Hamiltonian. This I is just the nuclear moment, how it's projecting along the Argand axis of the electrical field. So this is like the liquid droplet model of a nucleus, and it's subject to electrical field gradient, and it has a quadrupole moment. And you are expecting to see energy level structure like this. And so because we can directly measure these frequencies, that allow us to give you the parameters of what is the quadrupole moment of the excited state times the gradient of the electrical field? What is the quadrupole moment of a ground state times the electrical field gradient? Because these you can just directly read off from the energy splittings of the measurements we made. So this is interesting because you can take the ratio of those. You can remove the electrical field gradient of the crystal and will directly measure the ratio of the quadrupole moment of the excited state and ground state. Federica, I don't know if that's something interesting for nuclear physics. Yeah, we felt, it's finally precision spectroscopy can start to let you measure the nuclear structure a little bit. It's the first primitive level. But and you can do this is a so-called lab frame, but you can of course go transform this into the body fixed frame of the quadrupole moment, and you can actually calculate this intrinsic quadrupole moment difference between the nuclear excited state and nuclear ground state of thorium. For the first time, you can directly measure this with the 5 digits in experiment. And very surprisingly, when we actually go back to read the literatures of the thorium, we found out that people have been assuming the nuclear volume from the ground state and excited state is always the same. It's a little liquid droplet. Here's a nuclear model. Here's a nuclear model here, liquid droplet model. And the people just assume the volume of nuclears don't change when you go from ground state to excited, especially because the 2 states are separated only by 10 eV. But we are because we can measure the quadrupole moment difference, we can actually go back and calculate the volume difference, which is actually different at the 10 to minus 4 level. And why this is actually interesting or important is that because there have been a lot of discussions going on of probing new physics beyond the standard model, one of which is, can we turn these atomic clocks to be a search for dark matter? And one of the dark matter model is these are ultralight dark matter, which is basically a field, bosonic field, that can come in coupled to ordinary matter to change the fundamental constants, to turn them into an oscillatory field, oscillatory signal. And so if that's the case, people have been talking about, well, the fine structure alpha might depend on how much Earth is going through dark matter. Well, at least that's a probe or set a bound on what kind of a model that you're discussing. But in the nucleus, of course, this kind of a structure has a combined force of a strong force as well as a Coulomb force. So as I mentioned earlier, even though we are measuring an 8 eV energy difference of the excited state and ground state, but actually the configuration of a ground state excited state contains both QCD strong force and a Coulomb energy. And they just happen to cancel each other to the scale of 8.4 EV by accident. But the actual Coulomb contribution is actually 50 kilo EV. So imagine that alpha actually changes. Alpha is a constant, fine structure constant that governs how strong electron interacting with the electromagnetic field. And that's one of the key fundamental constants in physics. imagine that alpha is changing. That's instead of an atomic clock, which you typically have a scale of 1, the nuclear physics, because I'm actually measuring 50 kilo eV worth of energy, even though the transition is only 10 eV, I'm having an amplification of the potential detection of alpha being not a constant. So this will give you a more sensitive probe of a potential dark matter search. And it turns out being able to measure this volume difference and so on is important to constrain what is the Coulomb interaction energy, what's this amplification factor actually is. And I'm only talking about quadrupole. Of course, in nuclear physics, there's higher order moments. There could be octupole. There could be actually quite exciting time, because if you can measure octupoles and so on, then there's time variation. There's a CP violation stuff start to come in, because the octupole moments, it will not allow you to have a time reversal symmetry. And so this clock suddenly can connect to CP violating dipole moment search, like electron dipole moment and the nuclear dipole moments. And maybe coming to the end here, I want to tell you actually one really interesting question is also how well can a system like this be actually truly serve as a portable clock? And so remember I mentioned we can see those 5 transitions, and if the temperature of the crystal changes, the electrical field gradient of the crystal can change. The electron charge density could change. So that means these lines could be moving around. And this is the one worry. Yes, you said a crystal is portable, but when you go from the outside of the building to come into the building, well, the clock frequency might be different because temperature is very different. What kind of level of change are we talking about? So we did some preliminary probe on this already, temperature drift. We were able to change the temperature from, say, room temperature all the way down to 150 Kelvin. And you can see these lines actually shift differently. And one of the line has a very small temperature coefficient and hardly changed its frequency. And that's because it has 2 contributions. One is the quadrupole moment can interact with electric field gradient. The other contribution is due to the fact that there's electron density can also changing as a function of a temperature. So this line could be accidentally a line where the electron charge density changing is compensating for electrical field gradient change to make this line to be insensitive to temperature. But we don't want to rely on luck like that. If we want to build a clock that's actually stable, we need to do something else. So one proposal we already have is thinking about the self-calibration of a nuclear clock, where we are driving nuclear transitions here between the 2 nuclear states. But within each nuclear state, you can potentially do microwave spectroscopy like NMR. You can directly measure the energy difference between these nuclear states with nuclear magnetic resonance or nuclear quadrupole resonance with just coils. And typical frequency here is a few hundred megahertz. And that's a very typical sort of a nuclear NMR spectroscopy technology. So that will tell you the temperature coefficient. And this transition, in fact, has a sensitivity much, much smaller than the sensitivity of the frequency change within each manifold. So we think that you can use this technique to use magnetometer. It's almost like a co-magnetometer, co-electrometer to measure the energy splittings in each energy manifold of excited state, ground state. And then in the end, the difference between the ground state and excited state is actually very hardly dependent on the temperature, because we can servo that away, or we can actually measure things carefully. The final slide I want to end on is, besides the nuclear clock that's on the crystal that we showed, here the technique of being able to doping thorium into a calcium fluoride crystal has been powerful. And indeed, this is a crystal where we have shown very narrow transitions. It works. But it's a centimeter kind of scale crystal and requires about a few hundred microgram of a thorium in there. While if we can, this is something we have been working on in the lab, and we can actually make a thin film of just a few tens of nanometers deposited with vapor deposition onto a substrate made out of sapphire or and a platinum and something like that. Then it's potentially this will be a much smaller device. That would be very efficient use of a thorium material. You only need a microgram of the material, but we haven't seen narrow transitions. But I want to say the good news is that we have seen broad transitions by collaborating with the UCLA team of Eric Hedison. Remember, he has a laser that can have 20 gigahertz line width. And so we asked his laser to shine onto these thin films. And indeed, we were able to ship this to UCLA, and the UCLA team was able to recover the nuclear transition as well. And so it's a very promising starting point where why the thin film is particularly exciting is you can carry the thin film onto the airplane, and they cannot stop you because the radiation level is 1 banana or less. While it's a crystal, you still have to go through real nuclear safety office to be able to transport it between state lines. So this is something we were joking about. We want to make a nuclear clock to be truly, every citizen can have one if they want to. Then the thin film would be the way to go. And with that, I think I want to end on this notion that the nuclear clock sounds like it's just a clock making, can be very engineering, and I think of myself as a reasonable engineer. But I'm also very proud of being also a physicist, where lots of interesting physics ideas can come together. Could it be, of course, I'm very proud of precision laser metrology as one of the core missions of NIST for pushing metrology forward. But there's ultra-fast science, as you heard about. Attosecond physics comes in. The nuclear fundamental physics will come in. I think it's only just knocking on the door. We hope that this will stimulate much more work. But on the engineering front, the thin film stuff could really give us the scalable production and the photonics integration. I know that Mario, for example, sitting somewhere, a new member. We are the new class of this club, and Mario is an expert on photonics integration. So I think it's very exciting. That's the impression I want to leave for you, and thank you for your attention. Stay on.
Well, we have time for some questions. Would you please, if you can, stand up, tell us your name, and if you're a member?
Sure. I'm Bill Phillips, and I'm a member.
You certainly are a speaker member.
So I want to ask about the fundamental physics thing. So you showed us how if you were to see changes in these nuclear transition frequencies, and this could indicate a change in the Fine structure constant. But I guess, as you indicated, it could just as easily indicate a change in the nuclear coupling constant. So what I'm wondering is, what if you did one of your other experiments, which you do, where you're measuring different atomic transitions that have different sensitivities to the fine structure constant, but are essentially immune to any changes in the nuclear? If that showed nothing, then would you be sure that the other one was nuclear, or would there still be things you'd have to sort out?
Yeah, it's a really important question and a fair question. And indeed, I think this is in some sense you can say it's a probe, try to see if things actually are changing. You could be ended up seeing nuclear transition, atomic transitions absolutely rock solid with respect to each other. And if you see some difference, doesn't mean you can declare you made a discovery. It will require, just like LIGO, if they had seen a vibration in Livingston, they would never declare there's a gravitational wave. They had seen correlation. So we have been indeed thinking about, you probably needed to have a network, and you have atomic clocks, strontium against aluminum ion, strontium against ytterbium, and they have a different sensitivity on the order of 1. And so it's not a super sensitive, but if you see something on nuclear clock, you bet it will get people excited, saying, okay, now I'm just going to put my head down and just keep measuring to see if there's a difference there. And so I would say it's a signal rather than it's a confirmation. It's a trigger of excitement rather than, yes, we made a discovery. And so from that perspective, you want, almost like it's a little antenna, you want to turn it up to be as large as possible. You could be picking up a lot of junks, but it could also pick up a real signal at one point.
Yeah. Okay.
But it's really good. But also, when we put that paper out in June, there were 3 papers came on the archive 3 weeks later by German scientists and collaborating with Israeli scientists, and they were already putting bounds based on our observation. Even the line width apparently can't allow you to make a bound on the fine structure, fine fine structural constant change related to dark matter. So they actually put a paper on arXiv right away. And these are the things. I don't claim I'm an expert, and then we needed to like talk to nuclear physicists, talk to particle physicists to see what kind of a model, how much is the QCD physics that you are taking into account.
Red microphone.
Ciprian Ivanov, member. Is there a point at which an increase in scale of the nuclei being measured results in increasingly variable results?
Without increasingly,
An increase in the number being observed results in increasing variation of the times being measured.
you're basically saying how often I can run the nuclear clock? Is that?
Normally, a lot of things are measured at the same time in order to reduce variability,
Yeah.
but quite often there's a certain scale at which point things become more variable with more observations. Has that point been reached?
No, that point definitely has not been reached. Yeah, thank you. Sorry for being slow to understand your question. Yes, no, we have not. So what you're describing is a typical, statistical physics where initial measurements you're limited by statistics. So if your statistics is not good enough, your data points are so-called underscattered, and as you keep measuring, you're putting the statistical error bar down. Eventually, you'll start to see, my statistical uncertainty is so good. I start to see different measurements have a different, it start to vary above the statistical uncertainty. That's the so-called overscattered of data. My hope is as we continue to scatter less and less statistically, you will find out, indeed, that's how we actually figure out systematics. You will start to see data start to be overscattered. But then it turns out that overscatter is due to some lack of control of one experimental parameter. Like yesterday's measurement, I forgot to turn off my microwave. And so this is actually a way to figure out why data become overscattered is for a reason. And that's often is the way how you figure out systematic issues. And then once you figure out systematic issues, the data become underscattered again. And that's how the progress of atomic clock has been. You do much more precise measurements. I'm actually a big believer of precision because only when your precision is really good can you discover the scatter. The data between data points are scattered. And that's a way to discover there's a physics we do not understand. And once you understand it again, your precision gets better and the agreement gets better until they become not agreed again. And that's another layer of physics ready to be solved. Does that make sense to you? Yeah, thank you.
We're going to go to the blue microphone and then the red microphone. So Maria at the blue microphone.
Very interesting. Thank you. I know this is not ready to fix.
Name, you member.
Maria Zemankova, member. I understand the technology is not there to fix our grandfather clock that doesn't work. My question is about the precision and precision going into the future. Right now, we have the master clock at the U.S. Naval Observatory. Are you doing better than them, keeping the absolute time, and is it cheaper than what they are using? And that's one question.
That's one question, Maria. Yeah.
The other one is the Earth is slowing down.
Yes.
Now, if we are measuring absolute time, in some future, that absolute time is not going to be in sync with the Earth time. So what are your models doing for that?
Yeah, thank you, Maria. This is actually a very typical question for people like NIST people like myself. And the first one, the first one about Naval Observatory, and actually, in fact, NIST also keeps the official civilian time, Naval Observatory for military. But I would say that the strontium clock I talked about, but not just the strontium clock, any optical clock that's been in the state of the art, the performance is 10 to the 4 times better than the Naval Observatory clock. And you can say, what are we doing? Why are we still have Naval Observatory time? Well, that's because you need a lot of infrastructure, have all these microwave networks that you can actually, clock is not just for yourself, you need to broadcast to other people so they can compare the clocks. That's the whole point. The optical clock does not have that infrastructure yet. That needs to be built. We need to be able to, And I'm very proud to say NIST is actually leading that technology. Some of my colleagues in Boulder, Colorado, we start to compare clocks from my lab to proper NIST Boulder lab. How do we do that? We can lay fiber network between us, or the latest is to send a laser beam right in air between two laboratories over a few kilometers apart. And we had to, of course, get a city council approval so that the laser light is safe for birds. But we got that approval, and you can compare clocks at 10⁻18 levels across few kilometers. And our colleagues have taken that technology to the island of Hawaii, and they can connect 2 islands now. That's 30 kilometers. And now imagine you just point laser beam up, because 10 kilometers later, there's no more atmosphere. And so it's possible, in principle, we can do this today, is to connect the ground station optical atomic clock to a clock in the satellite. And if we can do that, the satellite can be in DC, can be in Boulder. That means your clock and my clock at 10⁻18 level can then be compared. This network kind of infrastructure will take time. This actually, and not only just for the US, this has to be a global thing if we want to have a time for all humankind, globalization of time standards. And that's exactly the discussion that's been going on. What time are we ready to switch from the cesium atomic standards to optical atomic standards? Is it a 2030? Or is it sooner? Is it later? So that's one thing. Okay, I hope that answers the first part of your question. The second part, remind me a little bit. The second part of your question is on. Can you quickly?
About leap second.
Leap second, yeah. So you said Earth time and atomic time. Yes, this has been around for now quite a while, and we know the Earth. Earth was great. Looking at the stars was great for keeping us time for a long, long time until atomic clocks invented, and you find out atoms swinging in a much more quantum mechanical way than Earth. Earth is very classical, and it is energy cost and so on, and does slow down, as you pointed out. And there has been a debate going on. There is a leap second where people say, every few years, I need to dial my clock back by a second so that I can keep my I can keep my sun on top of my head at noon. Otherwise, people feel weird. It's noon, but the sun is over there. But there's a debate. There's some pure scientists, mad scientists, will say, "Who cares where the sun is over there? I just want my atomic clock to keep the time for civilization for the next few thousand years." I think that debate. I don't know if that's been concluded, but the good thing is, for the next 100 years at least, will have a noticeable problem. If you say, I'm just going to give up my earthling time, I'm just keeping my atomic time, it won't be a major problem. So you can kick that ball down the court for your daughters and sons and so on to solve.
After the red mic.
They are going to suppress the leap second.
Yeah, exactly.
Yeah.
That's what I'm saying. At least you don't have to worry about in the next 100 years, the sun appears to be in a weird place at noon.
Red microphone.
Hi, I'm Alex Cronin, a visitor. What are the prospects to observe stimulated emission or rabbi flopping or Ramsey interference fringes? In other words, how coherent can the excitation be?
Yeah, Alex, thank you very much for this very important question. I may be ahead of myself when I said, well, we turn this into nuclear qubits. In order to do that, that means you have to drive, as you pointed out, you have to drive this transition in a coherent fashion. I can put it in arbitrary superposition on the Bloch sphere that I was showing you. We don't have that technology at the moment. Our laser is not good enough. Well, my laser, if you waited long enough, certainly it can be flipped up. The problem is there's decoherence. So as this spin is being flipped up, it's also doing dancing. So you never had a chance to really coherent. In order to do this, your coherent flipping rate has to be faster than the decoherence rate. And so we know all that trick. What's missing is a laser. And so our group, I think this route of going through idle second generation and so on has been powerful. And it made us, kind of right now, the only group who can do this. But I think it's not the future. One is it's not scalable. It's too big. So we have, unfortunately, again, when you have notoriety, when you have a CNN reporting, the companies actually noticed it. And so 2 companies contacted us saying, well, should we just go talk to DARPA together? I think, this is the company talking, okay, not me. The company was like, I think we have the technology right now for you, but we need some whatever, XX million dollars, and our company is willing to put in half of it. They were actually very committed. We're going to start doing this, and we'll get DARPA government funding. Then eventually we'll be able to deliver, say, 10 microwatts of CW light for your nuclear clock. I think that will be the starting point of all these coherent manipulations. All these things will come. Right now, our Rabi rate, if I estimate it, is about 5 hertz. The coherence rate at the moment, at least, that we couldn't see is 100 kilohertz. So it's clearly not good enough to do coherent flipping. But if we can, on one hand, I reduce my line width to kilohertz. On the other hand, I increase my Rabi rate to about a kilohertz. That's where I can do spin echoes. And all these interesting technology from atomic physics will come into nuclear physics. So it's a very important question. And believe me, this is something I really, really want to have next breakthrough.
I have a couple of questions from the chat box on the YouTube live stream.
Our first question from the live stream comes from Peter Bale, whose membership is unknown. With nuclear clocks pushing the boundaries of precision, what do you see as the biggest challenges in aligning external experimental components or the infrastructure that you previously mentioned to fully harness the clock's potential?
I think a laser, I actually think, well, going back to Alex's comment, I believe it's laser and it's integration, because if we can really understand in the next few years to understand the crystal physics, how much is the broadening, how much is the shifting, and I touched on this, but it's scratching the surface. But if we have, and it's actually hampered by the fact that our laser power is not very strong, so it's every measurement takes time. I will wish to have lasers can just flip the nuclear spin back, not nuclear spin, sorry, nuclear state back and forth really fast. Then I should be able to start to, I don't potentially can just distribute a lot of nuclear clocks across the continent and compare them. And that would be the first thing I was able to do. It's just much more portable. It's the scalability of being able to transport nuclear clock, I think, actually outweigh the atomic clock. But if you tell me, oh, a nuclear clock will immediately be more accurate than atomic clock, I'm not so sure, because atomic clock has, after all, gone through 4 decades of incredible quantum science revolution, and that's where we are today. And I still think we have a long ways to go. But nuclear clock can catch up really fast, especially with scalability of number of particles in there and the portability. I think those 2 are unique advantage of nuclear clock.
James Coe, member. And you talked about external perturbation and interference, and that nuclear clocks would be more robust, certainly here on Earth.
Yeah.
But what about in outer space, say beyond the Earth's atmosphere, or even on the moon, where you would have a high flux of cosmic rays? Now, I know that the energy transitions are rather low, but would these fluxes of cosmic rays cause more problem in outer space than they might on Earth? That's my question.
James, that's an extremely interesting question. I actually honestly haven't thought about. I thought you were going to ask what's going to be different on the moon. I think one thing is always going to be the same. Einstein's relativity is always going to apply. So the emotional effects and so are always going to be there. But electromagnetic field effect is much less. But now you're talking about high energy coupling. You're actually talking about, this is exactly where the excitement could be. Like could a nuclear clock be a neutrino detector? Those are the questions you can ask yourself. Indeed, because you are looking at higher energy sectors of physics, maybe you are opening up a new window of detection. And I just need to be honest with you. I don't know. I haven't thought about this, but there could be maybe it's almost the perfect time to segue to. You have had hands up for quite a while, but we needed two nuclear physicists to tell us this kind of coupling.
Michael Haken, a member from Silver Spring, Maryland, asks, how significant might time dilation variation due to shifts in Earth's interior mass distribution be relative to the anticipated precision of nuclear clocks?
How significant? Well, Well, if you're talking about interior of the Earth, is that the question was talking about?
I think so, yes.
Yeah. Well, I believe if you drill a shaft, you will continue to measure the gravitational redshifts, of course, and how well you can measure is just the clock precision. So I mentioned earlier, if you reach a precision of 10 to minus 20, you can measure time dilation at a 100 micron scale on the surface of the Earth. But as you go closer to the Earth, of course, the redshift will continue to persist, but it's no longer 1 over r squared, it's 1 over r. So the sensitivity you can calculate over what distance, and you can have a 100 micron sort of a level of sensitivity of seeing redshift. But if you can continue to push on the measurement precision, suppose I get to 10 to minus 25, then it's really interesting because over 100 nanometers, you will see time is different by the Earth's gravity. So now you start to think about what if I have multiple atoms that's distributed like this in the vertical, and their wavelength is covering on each other. And this is where quantum physics, because quantum physics, you don't know where you are. You're in a superposition of here and there, but then here and there, time is different. When you write down your Schrödinger's equation, you have a psi xt, x and t are the 2 independent variables. But now with that level of precision, x and t is connected. So there will be interesting, it's not a quantum gravity, but it's an interesting place where you start to see quantum physics in curved space-time. I joked with some of my quantum computer folks, friends in the industry. I said, in the end, the quantum computer has to live on a plane because that's gravity is the same. If you put it on a vertical direction, there will be decoherence due to the gravity because they are operating slightly different time phase. So I think, of course, that's a joke. The quantum computer would not care about that kind of a slow speed. They are chasing for fast speed. But for physics, this is quite interesting because you can start to see how macroscopic physics and microscopic physics start to touch in together. And you can even ask, is there one day you can actually see quantum gravity? That is really very far. I can actually give you one energy scale, perhaps, that would tell you how far we are. Suppose I have 2 atoms. My 2 fists are 2 atoms. And I put them in coherent superposition, ground state, excited state. So both are in coherent superposition. Both are doing this. But we know the ground state and excited state has a mass difference because excited state has h nu over c squared. It's Einstein's equation, E equals to mc squared. The excited state has extra photon in there. So that extra photon gives you extra mass. So if the 2 atoms are in coherent superposition, in principle, their gravity is in coherent superposition. And that effect you can see with clock, except that's at 10 to minus 45. but then you say, well, why don't I put 10 to the 23 atoms all nearby? You can dream about these kind of things. And the point is, if you start to have a quantum mechanical coherent superposition, and the gravity is also in superposition, as the precision continues to go to 10 to minus 30s, then maybe you'll actually see quantum gravity. And certainly not in my generation.
Blue microphone, Frederica.
My name is Frederica Darim, and I'm a member. Thank you for an excellent presentation on exquisite work. My question is, we talked about nuclear spectroscopy. Do you have nuclear spectroscopists knocking on your door to, in a sense, exploit your technology? And in terms of the infrastructure, is that going to be replicated in other locations so we can do the experiments? But also, in answering some other of the questions, maybe the technology is not totally mature. However, if you replicate it, then maybe the progress will be expedited because you're going to get input from multiple sort of to carve the directions of improvements.
Yes.
So what is the situation? Do you have people knocking on your door?
Yes, no, absolutely. I think so there's several layers to your question. One is on thorium alone. Thorium is a relatively easy target because it's only 10 eV. And there are now, I would say, more than a handful of the laboratory worldwide is building that technology that I've talked about. And indeed, they actually sent students over to our lab. There was a group from Yeah, Heidelberg. There's like a German high-energy nuclear physics facility, Max Planck, and they send the students spend 3 months and just learn that kind of technology. How do you scale the harmonic generation? And so I'm sure this technology is spreading. But I think another layer, I think a more interesting technology spreading would be if we invent CW laser that can do this, and then we're miniaturizing photonics and so on. And yet another one is to really truly have impact on nuclear physics. Thorium is just one accident.
Right.
We need to conquer the next one, which is uranium. And in the end, if you want to have this kind of using coherent light to do nuclear physics, you need to get a KEV, right? There's just all the nuclear transitions are up there. So once you open that up, it's just like a laser opened it up for atomic physics in 1960. That we are still very far. And I think there are technologies where people do free electron laser generations and so on. So we have had a lot of discussion with SLAC and so on with, can we use our laser to coherently seed their free electron laser as amplifier? And potentially maybe we can get down to 100 EV energy. My soft X-ray, I feel like perceivably within the decade we can do.
Maybe we have the director of Brookhaven National Lab giving a lecture 2 weeks ago, 2 weeks later, so we may ask her that question. What plans they have.
that would be great. I think it's opportunity for people who do tabletop experiments and a real big facility people to talk to each other. And can we start to think about coherent seeding? There's XUV frequency comb, put it into free electron lasers.
Thank you.
But I think this is a very, very important question. People start to think about these nuclear decays at a kilo EV scale, and how do we eventually, if you can do that, you are just universally now dealing with nuclear physics now.
Yep.
Yeah.
Thank you.
Sorry.
Is the red microphone somewhere? Okay, we have red, then blue.
Hello, I'm Joe Whalen. I'm a visitor. Thanks for the great talk. I just had a question, kind of a technical question about the UV comb. So these days you can buy a 1542 comb from Menlo that'll stay mode locked for years on end.
Yes.
And I was just kind of curious as to, I know you've been working on this for, I guess you said 20 years now. How turnkey is the high harmonic generation piece of the system? How easy is it? Can you just come in and, I don't know, open the xenon valve and you get ultraviolet light out or whatever?
Yeah, thank you. And so that's why it was at the very beginning, I want to acknowledge the students. And indeed, initially when we started this, the VOV comb was not very robust. And the thing that's always get damaged is mirror. Because you're putting tens of kilowatts of power circulating and you're generating high harmonics. If they hit on those mirrors, they can actually damage those mirrors. And over the years, we figured it out. You can put it, you can, initially, we did an experiment where every time we turn off the laser when we go home, we backfill with oxygen. I used to joke like oxygen bar for the mirrors to rehabilitate overnight. And actually, miraculously, they fixed the damage problem. And it turns out it's not by surprising because those coatings are oxygen bonds. And they're breaking those oxygen bonds. You can put oxygen back in. And then we figured, okay, why do you need to do that? Why don't you just flow oxygen all the time when you're doing that experiment? And that made it much, much better. Suddenly, we can actually, by the time we saw the nuclear transition, we can actually run our experiment 24/7. Doesn't mean it's always locked. It will occasionally jump out of the lock. It's a homemade system, so it will jump out of lock, but we can easily relock it and it can take time, take data. But it is homemade system. It's not replicated anywhere. It's not as robust. It's certainly not as robust as a manual system. But the main limitation is just bulky. It's not. If you want to call the clock, it's a shameful. It's a big device.
Blue microphone.
Bob Hershey, I'm a member. What further needs to happen to get people using this as a standard method?
Yeah, I think for this to be really being popularizing, I think we needed to definitely solve an integration problem. Like how do we On material side, can we show this crystal can work, and can we check all the systematic? So we need to do a lot of spectroscopy. Towards the end, I mentioned the thin film. I think a thin film, if that works, it would be much more promising. You can, when you do coding for a mirror, you can just put a dopes with some thorium in there, and you automatically have a mirror that has a thorium clock built in. And that would be just amazing. Imagine you can even build cavity QED, this quantum optics kind of a concept. So that has to happen. A lot of a material science study needs to happen to see how robust those nuclear transitions are. And then the other is the photonics. How is it possible to generate a laser that with sufficiently small footprint that can make a device that's maybe not much larger than a shoebox? I think at that point, I think it will be very popular. But so still a lot of work to do.
Okay, I think that'll be our last question. Before you go, we have a few small gifts of no monetary value, I assure you, so you do not have to declare this to the government.
Yeah.
Okay, so we have a framed copy of the announcement of your talk, and we have a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, which explains who founded the organization, why they called it the Philosophical Society. It wasn't to confuse all of us in the 21st century, and what the purpose of the organization was. And there are some interesting things about how a scientific discourse ought to take place that I commend to all of you to read. And then finally, we have a ribbon for you to wear. It has emblazoned on its side 3 stripes that are emblematic of the symbol for inductance, in memory of our founder, Joseph Henry, who is best known for his studies of inductance and for participating in the invention of the telephone and the telegraph. So with that, the actual items are actually in the back of the room. And thank you so much for this. Let's all have a nice hand for this terrific talk.
Thank you.
So before you go, we just have a few closing announcements. And before we adjourn to the social hour and the refreshments in the back of the room, the 2506 meeting will be on December 6th. The speaker will be, as Frederica mentioned, Joanne Hewitt. She is the director recently named of the Brookhaven National Laboratory, and she was the chair of the Particle Physics Decadal Survey. Well, I call it the Decadal Survey. They have a different name for it. But in any case, it is the study by the physics community of what projects should be and what priority for the next 10 years. A lot of it has to do with particle accelerators. And she'll be speaking on the state of and priorities for the future of U.S. particle physics. The 2507th meeting will be on December 20th, and because I'm behind, I don't know who that speaker is going to be. But there will be a speaker. On February 7th, Nick Lane, professor of evolutionary biology at University College London, will be coming from London to speak to us on his theories of the origin of life, which center on metabolic processes rather than RNA and DNA worlds. We are in the early stages of planning an all-day mini-conference on the JWST, which we will be held on Saturday, February 22, 2025. I can tell you that John Mather will be one of our speakers, and Massimo Stiavelli also will be a speaker. But we're in the late but early stages of our planning. On March 7th, 2025, Joanna Drucker, who's a professor in the Department of Information Sciences at UCLA, will be speaking about the origin and development of alphabets. And other meetings are, of course, being scheduled, so please check the website often for up-to-date information. Please join me in thanking the people who ran cameras, Robin Taylor in the back of the room, who sets things up and is running the live stream and the recording and turning the microphones on and off so we don't have crosstalk. So please, let's have a nice round of applause for everybody who helped out tonight. And with that, I will adjourn the 2505th meeting to the social hour. I wish everyone a good morning, afternoon, evening, or night, wherever you may be. And I want to thank all of the people who came, who are in this field, to make this particularly cogent and interesting lecture. Your questions were really great.